So we've been like narrowing down our focus in terms of like different types of trees. We started with a generic tree, meaning a tree that can have any number of children. We then shifted to a binary tree where it could have at most two children, and the left child versus the right child meant something, right? For Huffman and coding, it was 0 versus 1. For the decision tree, it was yes versus no. Today, we're going to do something even more specific, which is focusing on a binary search tree. It's often abbreviated BST because we love abbreviation, or that's not an abbreviation, that's an acronym. We love acronyms. And so what a binary search tree is the tree is sorted. So here's an example of a binary search tree where Juliet is at the root. And because it's a binary search tree, what this means is every descendant, every left descendant of Juliet will be less than Juliet when we think about it from a compare to method perspective. So we're dealing with strings here. So we're talking about lexicographic order, kind of like alphabetical order. So Adam, Eve, and Harry all come before in the alphabet Juliet, and Romeo and Tom come after. And that rule holds true at every node. So if we go down here to Eve, Adam comes before Eve, Harry comes after Eve. If we're over here at Romeo, Tom comes after Romeo. So it's a right child, not a left child. And this is how a binary search tree works. Um, yeah, this might seem familiar. So think about this for 30 seconds. Try try to connect this binary search tree to something else that we've studied in this data structures unit, the whole unit. Like where would this be helpful and where could we actually use this? So think about this on your own for like 30 seconds and then you're going to talk with your neighbors. All right, so chat with the person sitting next to you. What is this connected to? What data structure have we studied that behind the scenes might actually be a binary search tree? Any thoughts? What do you think? Priority queue. Wow, that's a really good question or a really good answer. I don't know, but I don't think so. I want to say I looked up the Java implementation of priority queue when we were studying that a while back, and it was a different type of structure, one that we don't study, like under the hood. But let me check on that. So could be, not positive. Yeah. What's that? An array? Um, Not really. An array is just when we have like a chunk of memory and we just put all the things in there one after another. Linked list. This is going to have the same structure as like what we've been coding. Like we're still going to have left and right, like for each node. It's not going to be just like a next. All right, we're going to hold on to that thought then. Yeah, you all will figure this out before we're done today. Um, I think this will, as we write some code, this is going to become more clear. So let's write some code to find a node in a binary search tree. I think that's a great place to start. So switching to our VS Code, I'm in the binary search tree.java file, binary search tree class. As always, I've written some Java doc for us to provide some context and save a little time. And we're going to write these methods together. Um, so only one instance variable, the root of our binary search tree. the constructor constructs an empty tree. Um, so we could leave this blank to be honest, but let's be explicit and say this dot root equals null. When the root is null, that's our definition of an empty tree, just like it was for the binary tree we wrote together previously. We're going to skip add for now. Let's do find first. So tries to find an object in the tree. We're past the object to find, and we're going to return true if the object is contained in the tree. So this method, basically, we say, hey, find this object and just let me know if it's in your tree or not. Return true or false. Okay. You'll notice that, again, our binary search tree is not a generic. We could have made it a generic, but we're going to keep it simple here. But note that it's not of type object, it's of type comparable. Comparable is the interface that often our classes promise to implement, and then we implement the compare to method. The reason why we have to have our objects of type comparable, the elements in our tree have to be comparable because that's how we determine whether we're going left or right. So we're going to have everything be of type comparable. All right, so down here in find, we're going to change this to do the find. So here's the common strategy we use when working with a tree in general and certainly a binary search tree. We're going to create a local variable called current, which references the current node we're looking at. Okay, so we'll initialize it to root because we're going to start at the root of the tree, and we're going to search for the specified object and see if it's in our tree or not. So we're going to keep searching until either we find it and return true, or we run out of nodes in the tree to look at, and in that case, we'll return false. So we'll set up a while loop while current is not equal to null. So that way, if the tree is empty, if the root is null, current will be null initially. We'll skip all this code, and we'll just say return false. All right, so that's like our condition for when we have an empty tree. Otherwise, we have to check and see if the current node contains as its data the object we're looking for. And I guess I jumped a little bit ahead of ourselves just to provide some context. We need to actually write the node class. I forgot about that because it's like so similar to all the node classes we've been writing, but let's do this. We're going to have 3 instance variables for a node, just like we have had for the binary tree, except the data will be of type comparable rather than of type object, because we need to be able to invoke the compare to method on it. And then, just like before, we'll have a left child and a right child, and those will be of type node. So this node class is identical to the node class we had in the binary tree, except the type of the data instance variable is comparable instead of object, because we need to actually compare the data, the element in the tree, against other elements. All right, so let's scroll back up to find. So what do we want to do in find? All right, well, let's check the current node and see if it's the object we're looking for. So I'll create a local variable called diff, like the difference. We can call the compare to method. So I'm always going to take the object we're searching for, and I'm going to invoke the compare to method on this, and then I'll have the actual, the data, the element related to the current node. I think it's helpful to be very consistent with how we invoke compare to. We're always going to invoke compare to as on the object we're like searching for or adding or removing, and we're going to pass as a parameter the current data always. And I'm going to be super consistent about that, because that way I think it matches the conceptual approach we have when we look at the tree. I think it's consistent with other things we've done. I love Kai Horstman and his text. In his code in the textbook, he writes it the opposite way. And historically, students have been really confused by that. So I just want to give you a heads up. This is different than how the textbook invokes compare to. And I think this will be better for you. Okay, so that's why we're doing it differently. But I don't want you to be surprised when you look at the text later. All right, we called the compare to method. The compare to method returns three different possibilities. It could return 0. So if diff is 0, we found the element. We found it, right? So they're equal. So we'll return true. We found the specified object in our tree. Otherwise, diff could be less than 0. And remember, going back to like APCSA, if compare to returns a value less than 0, that means the object is less than the current data, right? So you can replace the word compare to with either less than or greater than based on the value being returned being less than or greater than 0. So if the object is less than the current data, looking at our picture here, if the thing we're searching for is less than Juliet, we need to go left and search left. So let's write that. If diff is less than 0, we want to go left. Current equals current dot left. And then we'll keep iterating through this while loop and we'll keep searching. We are doing an iterative solution here for find. We are not writing this recursively. We could, but mixing it up a bit. Oops. Else, that means diff must be greater than 0, which means the object we're searching for is greater than the data of the current node. So we have to go right. We have to look in the right subtree. Current equals current dot right. Oh, this should be else if. I'm like, what is going on here? There we go. We will get warnings about type safety because we're not parameterizing our types because we're keeping it simple. We're going to ignore those for now. But those, we could do better. That's it. So we're going to keep comparing the node we're searching for against the current node in the tree. We're going to go left, we're going to go right, unless it's equal. Eventually, we're going to get to a point where when we say current equals current dot left or current equals current dot right, it's set to null because we're at a leaf, or there's no left or right child more specifically. And then we're done, we didn't find it. So this method will very quickly return whether the specified object is in the tree. Ring any bells yet, or do we need another method? Let's do another method. Great, so now we can search an existing tree. Let's talk about how we insert a node into a tree. So in this example, let's say we have an existing binary search tree with Juliet at the root. We have Diana, Tom, and Harry, and we're inserting Romeo. Inserting a node or inserting an element into a binary search tree is very similar to the find code we just wrote, extremely similar, because we're going to start at the root and we know we need to insert Romeo somewhere. We're not sure where, so we'll compare Romeo to Juliet. If Romeo is less than Juliet, we'll go left, but Romeo is greater than Juliet, so we'll go right. And now our new node is Tom. Like so far, it's identical to the find code we just wrote. We'll compare Romeo to Tom. If Romeo is less than Tom, it is. We'll go left. But if there is no left child, then that's where we'll put the new node. That's how we do the insertion. So let's write that code. So scrolling up just a little bit, here's the add method. We actually have to make a new node. So this code is very similar to what we wrote for the binary tree. We need to make a new node because we're given the data for the node, but we actually have to make the node that wraps around the data. Let's initialize everything about our new node. I like to be extra explicit, and even though it's going to be initialized to null, let's be super clear, like, yes, there is no left child. Yes, there is no right child. We set those both to null. And then we need to add it. We have to handle the boundary condition. We have to handle a special case where what if the tree is empty? That requires slightly different code. So if this dot root equals null, if the tree is empty, well, then it's really easy. We'll just say this dot root equals the new node and we're done. Wow, that's awful. Thank you. Else, not so easy. We've been exploring different types of recursive solutions, recursive strategies, perhaps I would say, in terms of how we can do stuff with trees. We've added recursive methods within the tree class itself. We've added recursive methods within the node class. In this case, we're going to do a recursive method in the node class again. I just want you to see lots of different approaches. And so we're going to defer adding the node to the node class itself. So I'm going to say this dot root dot add node, and I'm going to pass the new node as the parameter. So I'm basically telling the root of my tree, hey, node, add this node where it belongs, and here's the node I want you to add. So we're handling the boundary condition, the special case here, while deferring the rest to the node class itself. If we scroll all the way down to the node class, I've written the Java doc and the method header for add node. We just have to add in our algorithm. And the algorithm is going to be really similar to what we just wrote for find. We're going to create that local variable diff again, and we're going to compare the new node's data. Wow, I'm having the hardest time typing today. We'll call compare to against this node's data, which when we first call this method will be the roots data. And then we've got to handle our three different cases, okay? First case, the new node's data is less than this node's data, which means we go left, right? So new node is less than data. In our tree, we want to go left. All right, so let's capture that. If diff is less than 0, we have two different cases here. We want to go left. If the node has a child, a left child, then we'll simply recursively call add node with that. But if there is no left child, then we actually found out where to insert this node. So we need to have an extra if-else statement here. If the left child is null, hey, that's great news. We figured out where to add the node. We'll say left equals new node. Hey, we're done. Otherwise, someone else's problem. Hey, left child, you figure out where to add this node. And that's our recursive piece. The else if case, else if diff is greater than 0, super, super similar. If the right node is null, wonderful. We figured out where to insert this, set the right node to be the new node. It's no longer null. Else, guess what? Right child, you figure out where to add the node. There is a third possibility. The third possibility is that diff equals 0, meaning the node we're trying to add to the tree, or the element we're trying to add to the tree, got to be careful with my language. The element we're trying to add to the tree is already in the tree, right? If diff equals 0, it's already there. And if it's already there, we're just going to do nothing, okay? So we don't throw an exception. We don't return a true or false or anything. If we try to add an element that's already in the tree, fine, we don't care. We just kind of ignore it. Let's think about how fast this is. When we try to find a node, or when we try to insert a node, what characteristic of our tree determines the maximum number of comparisons we have to do? The height of the tree. Okay. Does anyone remember what the height of the tree is roughly proportional to in terms of the number of nodes? Yeah, log n. Okay. So finding an element in our tree or adding an element to our tree, from our big O perspective, it's like log n. It's really fast as n gets big compared to other algorithms. What data structure did we study where we could add elements and it was really fast? We could get elements and it was really fast. If we added an element and it was already there, it didn't throw an exception, we just ignored it. Is it a map or a tree map? Yeah, yes, almost. You're so close. It's a tree set. This is a tree set, right? So think back to sets. I know this is all the way in chapter 15, but sets, right? Hash set is the fastest, right? Remember that was order 1. But a tree set we used if we wanted to be able to iterate through the set in sorted order. Guess what? This is sorted order because it's a binary search tree. And the performance of our tree set was log n because it's based on the height of the binary search tree. This is how we implement a tree set. It's a binary search tree set. Okay. So this is cool. We're like writing a tree set. We're writing the tree set methods right now. We already wrote find, which is like the get. We already wrote add, which is like the add. So we've already got 2 of those methods down. There's only one method left in our set, and that's remove. So good news is there's only one method left. I mean, we'll write some other methods too, but in terms of the big 3 methods for a tree set, in this case, our binary search tree, remove is the last one. So that's the good news. The bad news is removing nodes from a binary search tree is crazy complicated. Okay. Here's why. And we're going to break it down into like small steps. There's a lot of different cases that we have to consider about where the node to be removed is in terms of the tree and how easy or hard it is to remove it. Because when we remove the node, the tree we leave behind still has to be a functional binary search tree. We can't like break the tree when we remove a node. So here's case 1. Case 1 is great. Case 1 is when the node to be removed is a leaf. It has no children. Okay. Where we run into complications is where the node to be removed has children, because if we just get rid of the node, we lose the whole subtree, right? All the children, all the descendants. We don't want that. So if the node to be removed has no children, this is actually pretty easy. So we're going to code the easy case first. We need to find the node to be removed. And then we simply tell its parent, hey, this child is now null because we removed this node. So not too bad. So let's do case 1 first. And we're going to break this down like case by case in terms of some comments as well. All right. So let's let's create a local variable to be removed, and we're going to initialize this to the root. And we're going to keep updating this local variable until it refers to the node to be removed. But for now, we'll initialize it to the root. In order to do this case in this algorithm, not only do we need to find the node to be removed, but we need to keep track of like who's its parent. So we're going to need another local variable where we can keep track of the parent. And the parent's going to start as null because the root has no parent. And we kind of need to keep track of like if we found the thing we're looking for. So we'll create a local variable. This will be like our sentinel variable. We'll initialize it to false. And now we'll do our search. This algorithm is extremely similar to what we just wrote for find and for add, but we need to keep track of more stuff. So we're writing it again. So we'll say while we haven't found the node and to be removed is not equal to null. Because it's also possible that the element, the object that's specified as a parameter might not be in our tree. And we might search through the whole tree and never find it, in which case we're done, right? So again, think of the set behavior. If we remove something from a set and it's not in the set, we don't get an exception. We don't get a failure. We just don't do it. All right, so now we got to do the search. Same code we've written twice before. The object we're searching for to be removed, we're going to compare it to be removed.data. That's like the current node we're looking at. And it's going to return, again, one of three types of values. If the difference is 0, this is great. We found it. Set found to true. This while loop will end because found will be true. To be removed will actually refer to the node whose data we want to remove. So that's wonderful. Otherwise, we still have to search. We're either going to look in the left subtree or the right subtree based on the value returned by compare to. But we also need to update the parent. So before we start changing what to be removed refers to, we're going to set the parent to be removed because we're about to jump down to its children. If the node we're looking for is less than the node we're at, we'll go left. Otherwise, we will go right. So this while loop we wrote is pretty much identical to what we wrote for the find method, except when this while loop ends, we will know whether we found the object we're searching for or not, and we'll have a reference to its parent if we did find it. So that's what makes it more valuable in this case. All right, let's give it a shot. Oh, let's handle the kind of boundary condition if we didn't find it. So if not found, just return. We're done. We were asked to remove an element from our tree. It's not in our tree. Great. No problem. All done. Otherwise, now let's do case one. So at this point, the parent is referring to this node. Node to be removed is referring to this node. We need to update the parents, either left or right child. We got to make sure we do the right one to null. So we have to write a little bit of code to make sure we update the right child, the left or the correct child, the left child or the right child appropriately. So for case one, we know we're in case one when we have no children. So if to be removed dot left is null and to be removed dot right is null, that's case one. We can say, we can check the parent. So there is another boundary condition here. What if the node we're removing is the root? And that's the only node in this whole tree. That could happen, right? So that means parent would be null because the root node has no parent. So let's handle the special case. If parent equals null, okay, this is kind of a special case. We're going to say this dot root equals null. Tree is now empty. We removed the root and there were no children. Else, if parent dot left equals to be removed. So if we're removing the parent's left child, we're going to say parent dot left equals null. Otherwise, we must be removing the right child, and we say parent dot right equals null. This handles case one. Yeah.
Like, how come you don't, for the it also parent dot left equals we don't have to do like dot equals or dot compared to.
Oh, excellent, excellent question. Okay, here's a really, really good question. Notice here, I'm using the equality operator and not dot equals or dot compare to. And the reason for that is here I'm comparing the actual references for two nodes. So the question I'm asking here is this instance variable left, does it refer to exactly the same object as the one to be removed is pointing to? Meaning like in our picture, I have a reference to this node. This right instance variable is also referring to this node. Are they referring to the same object? Are the references equal? Not like is the data the same? Because I'm not comparing like the data inside the node. I'm comparing the node references themselves. Is that helpful? Okay. Awesome, awesome question. All right, I'm going to show you a picture, but we're going to write the code tomorrow. Here's what's next. Case two says, hey, we found the node to be removed, and we know its parent, and the node to be removed doesn't have no children. The node to be removed has exactly one child. That's not too bad. This is harder than what we just coded, but not too crazy hard. Because if we want to get rid of this node, but we don't want to lose the child, we can instead tell the parent, hey, in this case, change your right child to refer to this node, right? So we get rid of this and we have the parent refer to here, which is the dashed blue line instead. So slightly more complicated than what we already coded, but not unreasonably so. So tomorrow we'll start class by coding case two. And then we've got one more case, which is what? What's going to be our third case? Yeah, if the node to be removed has two children, that's when it gets messy. So we'll warm up tomorrow with case 2, and then we'll dive into the hard stuff of case 3. It'll be great.